Well, good morning, ladies and gentlemen, and thank you, Mr. Chairman, for your introduction a short while ago. And I should also like to thank the Howard Foundation for considerable help over the years in supporting me while I worked in the University of Ulster. This is on the very north of Ireland, on the north coast almost. Where I'm working, where I do most of my carotenoid work now is in collaboration with John down at the opposite extreme of Ireland in Waterford. The weather is a little bit better in Waterford than it is in the north. I was asked to talk today about the measurement of macular carotenoids. John Landrum talked about the structure of the carotenoids yesterday, so he took that part of my talk away. Katie Meeher presented in 3 minutes our method of measuring carotenoids, one of the posters yesterday. So a large part of my talk has been taken. So I'm going to have to fill out with other aspects of the general facts about carotenoids rather than just macular carotenoids, though I will run through the method as well. The outline of my talk is to look at the factors that stimulated carotenoid research, the standard isocratic chromatography, chromatography specifically of zeaxanthin and mesozeaxanthin. The response, one of the questions that's come up yesterday quite a lot of times was the actual response or non-response to carotenoids. And I'll talk about that in the Irish studies because certainly the MOST-2, which John has described to you, the results were only available last week for the first time. And although we hadn't had the impression that there were any non-responders, I've looked more closely at that just to see whether in fact that impression was correct. And finally, I want to say something about the interpretation of plasma concentrations of the carotenoids. Carotenoid chemistry, as you're probably well aware, was the prerogative of organic chemists for much of the last century. They looked at the carotenoids in plants and foods and birds, and these were done by organic chemistry techniques. And really, carotenoid chemistry from the point of view of biochemists and nutritionists only became available, as John said yesterday, in the 1980s. Now, the main serum carotenoids were the specific interest of people, the provitamin A carotenoids in particular, alpha and beta carotene and beta cryptoxanthin being the main ones in the serum. The non-provitamin A, lutein and lycopene, interest in those was a little bit slower to develop. Now, this is a typical isocratic separation of the carotenoids from serum. It's one that was produced recently. Some of the earlier ones in the 1980s would have been far less sensitive than this. Nevertheless, the ones in the 1980s would produce the 5 main carotenoids. Lutein would come off very early in the elution, beta and alpha cryptoxanthin. Then you get the lycopene isomers, and then alpha and beta carotene. And finally, the last one to elute is an isomer of beta carotene. Now, where is zeaxanthin in all that? Well, in these chromatograms, zeaxanthin is underneath the lutein. So in fact, a lot of the early results, when they said they were reporting lutein, they were in fact reporting a mixture of lutein and zeaxanthin. An interest in separating the two developed later. This is obtained in a 3 microliter Cephedex column. Many of the early columns used were 5 microliters, which didn't give the separation that you see here. Now, why measure carotenoids? Well, the initial reasons for measuring the carotenoids from the nutritional community's point of view was the importance of vitamin A. Beta carotene, or green vegetables, green leafy vegetables, and orange and yellow fruits were the main source of vitamin A for most of the world's population. And so, interest in the amounts of beta carotene in the diet and beta cryptoxanthin in foodstuffs was of great interest. And consequently, nutritionists were specifically interested in alpha and beta carotene, beta cryptoxanthin. And before people had HPLC, Hoffman La Roche used to offer a service which would provide measurements of beta carotene, alpha and beta carotene. no one had any interest in anything else at that time. Interest in vitamin A was also associated with cardiovascular disease, because it was found that people with cardiovascular disease had poor vitamin A status. Now, you can't give vitamin A in large amounts because of its potentially toxic effects, but they thought we can give beta-carotene, a non-toxic carotenoid, in large amounts to people and prevent heart disease. Other associations found that smoking was linked to heart disease. Smoking depresses beta-carotene. Prospective studies of people at risk of heart disease or developing heart disease showed that they had low beta-carotene concentrations. So this considerable interest in giving large amounts of beta-carotene to prevent or delay the onset of lung cancer or cardiovascular disease generated those large studies done in the 1990s, which unfortunately had the unfortunate product of producing increased risks of lung cancer in the two groups where the supplementation study was done. And to my knowledge, there's never really been a satisfactory explanation as to why large amounts of a potentially non-toxic compound would increase the risk of cancer. A lot of hypotheses have been brought about, but it's not place to discuss those today. Interest in the macular carotenes. Why do we measure those? Well, to inform on the amount of lutein in the diet. They give information on the consumption of these proteins, of these carotenoids. Liz has mentioned yellow corn, maize, and egg yolk as being important sources. I noticed in her slides, although she suggested in the different ethnicities in America that there was very little difference, some of the earlier results that produced suggest that in fact blacks in America were getting 3 times the amount of lutein in their diet. And this was attributed to the large consumption of yellow corn. I think Liz's data is probably more up to date than those earlier studies, but certainly yellow corn is an important source of beta-carotene. Of lutein. Now the carotenoids, you've seen these structures yesterday from John Landrum. The important point about them is that beta-carotene at the top there is a good source of vitamin A, because if you split across the central double bond there, you produce 2 molecules of retinol. This beta ion structure with a subsequent conjugated chain is the relevant factor from vitamin A nutrition. Where it occurs in a carotenoid, it is a source of vitamin A. So with alpha-carotene, you have the structure here. With beta-cryptoxanthin, you have the structure here. So these are sources of vitamin A. Now, as John mentioned yesterday, and I'll repeat this, beta-carotene, if you hydroxylate the 2 ring molecules, you produce zeaxanthin. And beta-carotene has got a symmetrical series of conjugated double bonds, which is longer than any of the other carotenoids. And so that increases its antioxidant potential, plus the other factors that John mentioned about the stereochemistry of molecules and the position of the hydroxyl group. Right, moving on. Well, the expanding interest in the non-provitamin A carotenoids generated by the work of Bone and Landrum in 1985 and 1983 stimulated us relatively recently to look more closely at these 2 compounds and to try and separate them. They did present problems. Again, you've seen this slide, so I won't go over it again. But just to mention that the zeaxanthin and mesozeaxanthin are mirror images because of the symmetry or the asymmetry of this particular hydroxyl group, one coming out from the plane of the molecule and one going back from the plane of the molecule. What were the challenges involved in setting up a method for mesozeaxanthin and zeaxanthin and lutein? Isocratic chromatography, as it was being done for beta-carotene separation and by many workers in the 80s and 90s, was not very good at separating zeaxanthin and lutein. we started looking at this, looking at longer columns, gradient chromatography, modifying solvents. And then, fortunately, we came across a work of Richard Bone, where he used a Phenomenex column, 3 micron, 25 centimeters long, and found that it did, in fact, separate very nicely lutein and zeaxanthin, and so we adopted that method. And that was the method which we set up in Ulster, first of all, and we're now using in Waterford. That is the separation taken from a serum sample. You can see lutein coming off first. It's almost baseline resolution in many samples, and if zeaxanthin and meso are present, then they will both come off second. If only zeaxanthin is present, then that is in the same position. We cannot separate the two zeaxanthins using this technique, but we can quantify the amount of total mesozeaxanthin and total lutein using this technique. Unfortunately, this method had a problem. It took at least 80 minutes to elute beta-carotene. And you can't start the next chromatogram, if you're only interested in these, at 10 minutes, because that beta-carotene is going to come through and the later carotenoids are going to come through in your next chromatogram. So initially, because we didn't have time, we used the method as it stood, and we just spent a long time doing chromatography in order to get our measurements of lutein and mesozeaxanthin and zeaxanthin. Now, as I said, we've introduced this method down in Waterford, and we've modified it, as Katie would have described yesterday, down to about 25 minutes by using part isocratic and part gradient chromatography. Initially, we use isocratic chromatography, that is, we just have a single solvent mixture, and at a constant flow rate of 0.8 mils per minute. We have dropped the temperature to 15 degrees because we get slightly better resolution using that. And then at round about 12 minutes, we set up a gradient. We bring off the internal standard very soon, and we change the gradient even more after that, and the system is finished within 25 minutes. It's still long by comparison to many of the screening techniques, but it's the best we can do at the moment, and it is working well. Okay. So how do we go about measuring mesozeaxanthin? Many of you will probably be aware of this technique, but for those of you who are not, what the technique we're using is to watch the monitor of the Phenomenex separation. And when we reach this time point here, we start collecting the effluent from the waistline. When we reach this time point here, we stop collection. Now, that is a very crude way of collecting the zeaxanthin fraction, because obviously what is happening at the waistline at the time point you're seeing here is not this particular situation. Some of the lutein is coming off at that time point. And likewise, when you stop here, some of the mesozeaxanthin will continue to elute after your collection. So you don't collect a complete fraction, and Katie described that very well yesterday. And we're looking at ways of improving that, but at the moment, that is our technique. Having collected the effluent, we get 1 mil, and we evaporate to dryness. We reconstitute then for the chiral chromatography as the second part of the assay. Chiral chromatography, these are mirror images of each other, as was described yesterday. I don't think I need to say any more about that particular slide. The principle of separation is in many ways very similar to ordinary isocratic chromatography. You are delaying certain components in their elution and allowing others to throw through more quickly. And the way you do that in the case of isocratic chromatography is that you use a polarity separation, so that your more polar substances come off first and your less polar come off later. In the case of chiral chromatography, you have a system whereby you try to bind the enantiomers at different, which have different stabilities in terms of their binding ability. Obviously, that optically active point of binding, that hydroxyl group, is going in different directions in the two molecules. So if you're binding at several points on your stationary phase, then one is going to be different to the other. So the more stable one stays on the column while you elute the less stable complex. It's said that you need to achieve discrimination, you need to have at least 3 points of interaction between the molecule and the solid phase to achieve chiral recognition. Now, the two main factors influencing resolution on a chiral column are the mobile phase that you use and temperature. Low temperature will increase the binding of the enantiomer, or the stability of the complex with the solid phase, but it's suggested that it may actually make it worse. In fact, you get overlap of your system and broadening of the peaks. So in fact, it's a question of finding out what is the best system. For us, we found that 15 degrees gives us a reasonable flow rate of the compounds and gives us a reasonable separation. Now, the initial report that Liz has just mentioned by the initial report of a separation of these two isomers by Macular, he used chiral chromatography, but in fact he combined benzoic acid with the meso and zeaxanthin isomers. This produced a larger compound still, and he was able to separate his enantiomers using this particular column, shown here, the Supimax OA2000. This is also a chiral column. It is now possible to separate the two compounds directly using a chiral pack, AD column, without derivatization, and that is the technique which we're currently using and which initially I used in the north in Coleraine. So the separation. This is the separation we're currently getting. You see meso coming off first, followed by zeaxanthin. It's nicely separated from lutein. So although lutein invariably contaminates our sample, it is nicely separated, and so it doesn't interfere with the assay. Because what we do with these two compounds is we work out the proportion of each isomer in the total eluting fraction. Now, we've quantified the total amount of mixed isomers in the first part of the analysis. So using the proportions we obtained from the second analysis, we can determine the concentrations of the individual zeaxanthin and mesozeaxanthin. And the details of the separation are shown here. It's gradient chromatography, run at 0.8 mils per minute, 50 degrees centigrade. A reasonable separation. It's certainly not baseline separation, but it's a fairly clean distribution of the two peaks and a clean separation from lutein. And the calculation procedure, which I've just described, is shown on this slide, so I won't say anything more about that. Now, I said the next aspect I was going to look at was actually response or non-responders. I looked first of all at the work we did in Ulster. This was an intervention trial with lutein plus, which is roughly equal amounts of lutein and mesozeaxanthin and a small amount of zeaxanthin. The responses we got are shown here. I've not shown zeaxanthin on this slide, just meso and lutein. And what you can see is that there is a clear difference between men and women for both lutein and for mesozeaxanthin. In each case, women seem to take up the carotenoid better than the men, or at least the response in the plasma. Now, everybody, and this was a trial of 21 people. We had 10 women, 11 women and 10 men. We supplemented for 21 days, and everybody responded. There were no non-responders. And you can see there are time effects, time gender, the rate of increase is different between the genders, and the genders differ in the amounts. So there were no non-responders in these 21 subjects. These slides you've already seen from John earlier yesterday, and from Katie on the posters yesterday as well. Now, as I said, these results were only available last week. It was our impression that there were no non-responders. Now, in fact, there were a few non-responders. I went through the data last night, and this is what I found. For those who were supplemented with lutein, zeaxanthin, the top row there, the bulb's gone at the moment or something. There we are. Mainly lutein, very little zeaxanthin. We had 2 non-responders out of the 23 subjects. For those getting lutein, zeaxanthin, MZ, the 10 to 2 to 10 milligram mixture, we had again 2 non-responders. One who didn't respond for lutein, but did respond for mesozeaxanthin. And one who didn't respond for mesozeaxanthin, but did respond for lutein. And then finally, in the other group, we had again 1 individual. Most of this is mesozeaxanthin. So although there were 18 non-responders for lutein, there's very little lutein present, and it was, maybe we shouldn't have expected much of a response. Though at 2 milligrams, certainly Bone and Landrum have reported responses. Anyway, looking at this individual showed no response for mesozeaxanthin and no response for lutein. So of this group, we have 5 who show some evidence of no response. 2 here and 1 here, completely no response. And 2 here with a partial response to individual carotenoids. I've really not had time to make any head and tail of that to find out what it tells us. And we're still working on that one. In terms of response, how do we quantify what a serum value means? Well, I think there's some very nice data available. There's probably data from others as well, but there's 2 very nice publications which came out from Hartman and Thurnham. This isn't me, this isn't a spelling mistake, this is somebody else. Hartman supplemented with lutein at 2 levels, 20 milligrams and 4 milligrams of lutein for a very long period of time, for well over 40 days. And likewise, Thurman did a similar experiment using 10 milligrams and 2 milligrams of zeaxanthin. What they both showed was that there was a plateau effect after approximately 18 days, 18 to 21 days. After that time, there was no further increase. So I've plotted those plateau concentrations on this slide, and as you can see, I think somebody said earlier this morning, there's a fairly linear response to both zeaxanthin and lutein. I forget why that one's a different symbol. Never mind. For the moment, we'll ignore that one. What I wanted to show you on here was that we looked at our mesozeaxanthin response in comparison to the other 2 things, and you see here we supplemented with 8 milligrams of mesozeaxanthin. Oh, that was the lutein response. In the supplement that we used in Ireland, the lutein plus supplement, lutein was here, mesozeaxanthin was here. So mesozeaxanthin is giving a lower response than either zeaxanthin or lutein, and this was from the lutein plus preparation. Early results suggest that, in fact, the MacuShield preparation gives an even lower response than does the lutein plus response, but we're still working on that aspect of it. So you can use the concentration in the plasma to give you some indication of how much people are consuming. And if you look at this data, you can see that the amounts Dr. Johnson was telling us about, that the consumption of lutein is around about 2 to 4 milligrams in the population. This equates to the sort of concentration that you find in a population, around about 0.2 to 0.3. So it's a useful marker to interpret data. What complicates this sort of interpretation? Well, inflammation, and this is the last topic I want to talk about, inflammation interferes with those relationships, because inflammation depresses carotenoids. There are numerous reports of smoking being associated with reduced levels of beta-carotene. I mentioned them earlier on when the interest in heart disease story. Disease itself has a precipitous effect on, or appears to have a precipitous effect on serum carotenoids. John Landrum mentioned the chickens yesterday who were infected with disease. The lutein, as it almost washes out of the body at the same time. There's a report on chickens and Newcastle disease, and lutein appears in the urine and it just disappears from the blood. Now this is a human experiment, not an experiment, a human observation by Sear, a Hungarian worker, who compared infants with infectious disease against controls. Now, human experiments are always difficult to interpret, because the children who are in hospital with extremely low carotenoid levels may not have been comparable to the controls who he compared with. They may have had low values before they came into hospital. But the chicken results certainly alert us to something that's going on with respect to inflammation and carotenoids. Finally, subclinical inflammation. This is something which most people forget about. In this room, there will be people who have evidence of subclinical inflammation. And as a consequence of that, their carotenoids will be depressed. There won't be many, perhaps 1 or 2%. But there will be some people. And if you go to parts of the world like Africa, you can have as many as 90% of apparently healthy people with evidence of subclinical inflammation. I'm going to show you some data we got from Kenya in patients who, not patients, they were perfectly healthy, apparently healthy people living in the community who had been tested positive for HIV. They had no evidence, clinical evidence of disease at the time we were studying them. It was a supplementation study. I'm just looking here at the baseline data. And what you see is that we use CRP and AGP. This is another acute phase protein. I'll tell you why we used it in a minute. In those with a raised CRP, beta-carotene slightly elevated, alpha-carotene depressed, lutein starting to be depressed, lycopene depressed. Where we've got both acute phase proteins, everything is depressed. And where AGP is only the increased acute phase protein, we have some sort of restitution. Things are starting to get better, starting to go up again. Now, why have I divided them like that? Well, it's based on the model of what those acute phase proteins represent in terms of a disease. This is the model, and what you see happens when you get an infection. Your CRP rises almost instantaneously. As soon as you get bitten by a mosquito, injecting malaria parasites, then your CRP will rise. You may get no evidence of clinical disease in the first 24 to 48 hours. And this period we call our incubation phase, where you've got evidence of CRP increasing, but no evidence of clinical signs. Then you get sickness, variable length of time, variable severity. You don't take samples from people who are sick because you know it will not give you a good measure of nutritional status. Once they start to get better and the clinical signs disappear, then CRP normalizes very rapidly. CRP comes back down to normal. AGP, however, shows a different performance. AGP rises slowly. During the incubation phase, it's very often not gone past normal. It rises through infection, and in convalescence, it's elevated. So you can divide any population into 4 groups. Those in the reference group, where there's no raised inflammatory proteins, those with a raised CRP, those with both raised, and those with only AGP raised. This reflects the severity. At this time point, this is when the effect of disease has had its greatest effect on the carotenoids or the other nutrients which you're looking at. Vitamin D, ferritin, vitamin A, vitamin C, pyridoxal phosphate. Many nutrients are influenced in this fashion by this inflammatory response. So the important thing is here that apparently healthy people can have evidence of subclinical inflammation. Subclinical inflammation will disturb the relationship between how you interpret the plasma concentration in terms of a dietary intake. So in conclusion, just quickly go through this. Serum carotenoids inform on a patient's diet. Lutein is the major carotenoid in the diet, which is useful for macular. Zeaxanthin, MZ, minor constituents. From what Dr. Johnson would suggest, MZ is probably not in the diet unless you're living in Mexico or in parts of California. LZ and MZ have the same molecular composition, two-stage processes needed to quantify. Isocratic reverse phase HPLC quantifies L and the mixed Z, and chiral chromatography provides proportions of Z and MZ. And in that way you can get measurements of these 3 carotenoids in the serum. And the interpretation can be hampered by inflammation, which depresses serum concentrations. Thank you very much.